Okay, so I'd like to begin with thanking the organizers for the invitation to this very nice workshop. So I had a fairly generic title, so here I thought I'd show a layout of what I'm actually going to talk about. Sorry, you go for it. It's okay. So I'm going to talk about two different materials, one osmate with 5D3 and an iridate, so that we've all seen already, Strontium 2 iridium O4 with 5D5. And I'll present neutron scattering and resonant X-ray measurements to look at the magnetic ground states and the excitation. Okay, I'll begin with a very brief introduction too. Okay, so this work has been going on for some time and has involved a lot of collaborators. I just want to list them all up here and point out where the work was done at Oak Ridge, the spallation neutron source, the high flux isotope reactor, as well as synchrotron sources. Okay. So you've seen this slide before, a similar slide, where we have this general motivation that as we go from 3D to 5D transition metal oxides, there's a change in the competing interactions, and this can lead to a variety of novel behavior. So I'm going to specifically focus on these two materials, the 214 and the osmate, which have interesting insulating properties and interesting metal to insulator transitions. Okay, so here's a very sort of cartoonish slide about the two metal insulator models that I'll be talking about in this presentation. So on the left is the MOT, metal insulator transition, that you're all familiar with, where you have U and the hopping parameter can lead to a splitting of the band. You can drive an insulating ground state. And this was proposed way back in 1949. But recently, about 10 years ago, there was this paper on Strontium 2 iridium O4 that showed you can have a new type of MOT insulating state that's driven with spin-orbit coupling and the Coulomb interactions. And then the alternative end of a potential metal to insulator transition was proposed by Slater, where magnetism alone is the driving factor to create an insulating ground state. This is typically continuous. The magnetic ordering has to occur at the same temperature, and you need to have a certain type of magnetic order that creates a periodic potential that can localize the electrons and drive the insulating ground state. So in the Slater model, you have these ordered moments that create a mean field that confine the electrons, and there's been some debate that perhaps this is maybe better described as a Lifshitz type transition, where you need the small u and large hybridization that can renormalize the Fermi surface. But in any case, what I'm going to be talking about for this sodium osmium oxide is a magnetically driven or magnetically coupled metal insulator transition. And I'll touch upon what is actually happening to the electronic ground state as well, since we have 3 electrons. Okay, so the first part, Strontium 2 iridium O4. So you've seen similar plots to this, but I'll just recap the important points for this talk. So it's a layered perovskite structure. It actually has a space group number 88, so slightly lower symmetry than was previously reported. It orders antiferromagnetically at 240 Kelvin, and the spins follow rigidly the canting of the octahedra in the AB plane. So this is looking down the AB plane. If you apply a magnetic field, you have a magnetic structural change, where the different layers create a net ferromagnetic component. Okay, and there's been a lot of investigations into this material. So here's just some examples. So what I'm interested in this investigation is the somewhat surprising similarities between Strontium 2 iridium O4 and the cuprates, specifically lanthanum 2 copper oxide. So if we compare these two materials, they have very similar magnetic and crystal structures. They're both MOT insulators, driven by slightly different mechanisms. They have spin-a-half or pseudo-spin-a-half moments. And perhaps the most compelling evidence of the most intriguing fact of their similarities is found when you look at the spin excitations. So here, for Strontium 2 iridium O4 is the Rix data, so momentum against energy. And for lanthanum 2 copper O4 is the neutron data. They look very similar, and they've both been described within this isotropic 2D Heisenberg model. So the similarity is perhaps surprising, since you have a large difference in the spin-orbit coupling value. For the cuprate, spin-orbit coupling is really just a small perturbation. For iridates, as we know, it's often central to the physics of the system. So if you have a large spin-orbit coupling, this introduces anisotropy into the system. And a signature of this would be a spin gap in the excitation spectra. So there's been various papers, basically one every year, that's tried to define the spin gap. And it's varied from very small to around 20 MeV.
So why is this isotropic and why is it Heisenberg if there is gamma and D?
Okay, so I guess you can.
I was on the paper, so because they were small.
Yeah, you sort of ignore them. I guess you can ignore them. Yeah, okay. So the 2 points that I'm going to hopefully convince you, or at least start to look at, is this model applicable? Can we use a 2D isotropic or anisotropic model? And what is really happening in this low energy region? Can we access the spin gap and then try and understand the anisotropy? Okay, so the most straightforward measurement is to do neutron scattering. It's extremely powerful. You can map out all of reciprocal space and energy with low resolution, sub-MeV resolution. And what you measure, you can model exactly. But there's challenges for iridates that have stopped this happening. So they're typically small crystal sizes. For neutron scattering, especially inelastic neutron scattering, you need large mass of the order of grams. Iridium is moderately neutron absorbing. It's not terrible, but if you go through more than a few millimeters of sample, you'll absorb most of the neutrons. And the big problem is you have this small moment. So you have a small signal fighting against a small crystal in an absorption. So what we did was we grew a lot of small Strontium 2 Iridium O4 crystals. Actually, the one in the middle is a very large, or relatively large, of around 0.3 grams. But we co-aligned, it says around 100, I think there was 97 crystals to have a total mass over 1.1 grams. Here's the ordering of the magnetic Bragg reflection, showing that the whole array orders continuously together. There's no different onset of ordering temperatures. To overcome the neutron absorption, we did the measurements at the SNS, the spallation neutron source. So here's a picture of the detectors. There's 2 people sitting in the beam stop, I think it is, when it was being built. So these are very large, meter-high detectors. So it means that we can have the crystal essentially flat. The neutrons go straight through the thin C-axis of the crystal, so only less than a millimeter. So we can get over this absorption. And all of this combined should hopefully allow us to get a large signal to get over this small moment issue. Okay, so here's the data shown here, where we have the in-plane momentum, the H0 plane against energy. So, and this is the elastic line, this red down here. So here you can see we have clearly defined inelastic excitations coming down to below 5 MeV. Okay? And if we take a cut through the energy, so this is an inelastic energy of 7 MeV in the HK plane. So this is looking within the AB plane of the material. We can see we have clearly defined spin excitation. So we have momentum resolved dependence, so clear correlations within the AB plane. If we do this similar thing looking now along the L direction, you can see we have this very broad streak of scattering. So this is the same inelastic energy. A very broad scattering. Essentially, if we take a cut, a 1D cut, essentially no L dependence. So this is saying that the correlations between the planes are very, very weak. And we can essentially ignore them. So this means that we really are in this strongly two-dimensional limit for this Heisenberg model. So this has sort of been assumed before, but neutrons provide a direct measurement of this. Okay, so we continued on. So Rick's resonant inelastic X-ray scattering has looked at the excitation spectra. We wanted to really focus in on this low energy region. So this measurement here with Rick's was with 100 MeV resolution. There's been further measurements with, I think, 30 MeV resolution, but still it makes it very challenging to get down to this gamma point and to try and understand if any spin gap exists. So we measured up to about 80 MeV with neutron scattering. We were able to model this using this isotropic model, and we see very good agreement. So these are intensities just taking cuts through the dispersion coming out of the zone center. Okay, so we wanted to look at the low energy excitation. So for this, we did a measurement on a cold neutron chopper spectrometer that has a measurement resolution we had was 0.1 MeV. You can go even lower than this to sub 0.1 MeV resolution. At 1.5, you can inelastic energy. You can see there's a clearly defined excitation. So if we look at the scattering around the zone center from 0.4 MeV up to 2.25 MeV. If we look any lower than 0.4, we start to hit the elastic line, and that smears out the data. We can fit the scattering just to the Gaussian, and here are the points in red shown here. And if we fit this, we're able to extract the value of the spin gap for this material, and we can define this fairly accurately as 0.6 MeV. So, oops. So, yep.
so when I see you
Yeah.
draw this broken line.
The dashed line. Yeah. So
it doesn't follow at all because I see as if I have two.
Oh, okay. So.
Two or three peaks.
Okay.
Interpret that.
So the dashed line is fitting the model with the instrument resolution. So we're attempting to fit this data, and which is extracted from these 2D cuts here, which I admit is it's slightly noisy data, but I think it's still, I think the correspondence is still sort of compelling.
This is because you have iridate and this varies. So
it's just you have a very, very small signal, yeah, so there's around about the same time that we published this work, there was another measurement, and they didn't use these large detectors. They just did a triple axis measurement, and basically they couldn't even see anything below 2 MeV. So yeah, it's not great, but it's the best we have. Okay, so yeah, there is a very small gap, but essentially on the order of the excitations, this is we can use this simple two-dimensional isotropic Heisenberg model and map on the physics to the cuprates. Okay, so if you want to go a little bit further to see what happens if we tune the system, if we can dope. So this is sort of continuing on from the previous speaker, where here are the various dopings that have been tried. So yeah, copper has been tried. So the various dopings that have been tried, rhodium sort of scared us, so we did ruthenium, which in some way should be a nicer, cleaner isovalent doping, should go in as ruthenium 4+. So here's the previous, this series was investigated by Bob Cava back in 1994, where at around 0.5 or just a little bit above that, you have a structural transition. So we're going to focus on this lower doping region. This is the iridium to ruthenium with X. We're going to focus on below 0.4, where you can see there's a slight driving from an insulating state down to a metallic state. Okay, so here are some results just to check what the doping is actually doing. So the top is the paper by Kim, where this is a resonant elastic X-ray scattering. You have a large enhancement at one edge, suppressed in intensity at another edge. So this is a signature of a J effective equals a half state. It's not a definitive measurement, but it's a signature. So for the X equals 0.1 and 0.2 ruthenium, we see the same behavior. We performed absorption spectroscopy and XMCD to get a little bit more quantitative information on the J effective state to see that it's still present, it's still there. And we looked at X-ray absorption spectroscopy, or XANES, where this is for 0.05 doping of ruthenium, 0.2 the pure compound, and a standard iridium oxide. You can see that the position of the edge, the energy of the edge lines up exactly, so they're all the same valence, so they're all iridium 4+. Okay, so we have the same J effective state, we have iridium 4+. We wanted to see if this is doing anything to the magnetism, or are we just putting ruthenium in and essentially just diluting the system? Well, so we performed polarized neutron scattering measurements and polarized X-ray scattering, resonant X-ray scattering measurements to try and understand the ground state. And here's the phase diagram that we get out. So essentially, as we put in ruthenium, so this X is ruthenium, we have this M1 phase, which is just the parent magnetic structure. But as we cool the temperature down, we go into this other phase where we have spins aligned along the C-axis. So, and then as we dope further, we go into a region where we just have C-axis aligned spins. So this is sort of, we looked for any type of structural phase separation. There was no evidence of that from neutron or X-ray scattering. We don't see we don't see doubling of 2 theta peaks. So we believe that this is most likely electronic phase separation that has been found in the 327 as well. So, and this is causing a sort of a very unusual phase diagram.
I'm sorry, what do you mean again by M1 plus M2?
So this is M1. It's just labeling of the magnetic structures.
M1 plus M2, what do you mean?
So this has, if we do a measurement, we see both magnetic phases in this region. We see diffraction peaks from both. Yeah.
So what is the cause, the origin of this turning of the spin?
That's a good question. I don't know.
You didn't, let's say, inspect it. Let's say any specific change in the spin-spin interaction. Right?
Well, so I'll show the excitation next. Mm-hmm. There. So so here's the RIC spectra, resonant inelastic X-ray scattering, on the 0.2 case. So this is where we're just in this regime of the C-axis aligned antiferromagnetic spins. So we've subtracted out the elastic line and then taken cuts to give the data points, the red circles shown here, varying through different regions in the Brillouin zone. So the dashed line is what you would expect for putting in the parameters for Strontium 2, iridium O4. You can see that we're clearly shifting away from this. And if we just apply linear spin wave theory to the data we have, we get a J reduced to around 42 MeV, J primed, slightly reduced, and we don't need to include any J double primed parameter. Yeah. So next nearest neighbor and furthest nearest.
So this means that you can fit the spin wave excitation without including any Jaruzinski-Moria interaction, which is there and
so,
it's huge. I mean, it's not huge, but it's quite substantial.
Yeah. So there's a gap that we introduced the anisotropy. Yeah. Yep. So there's that's one of the main points is you have this. So this was measured with a resolution of 30 MeV, 35 MeV, and it looks like there's a gap of 40 MeV. But so obviously this is down to fitting and interpreting the data. So
J prime is also an isotropy there.
Yeah. Sorry, you're right. Yep. Yeah, I missed that out. Sorry.
이거 괜찮은데 이제 도핑 이제 밸런스로 리듬이 change. That case is no longer spin J 3 half 1 half the J half region or J1 or that case is anisotropy is also important, right? In the iridium 5 plus case is single ion anisotropy is also part of the other type of.
Sure. What's your question? Just. Okay. Well. So when we dope it, I don't need to go all the way back, but it's still iridium 4 plus. So we have this. I'll go there. This shows that the valence state for doping. This is what we're looking at. Ruthenium 0.2 is exactly the same as the valence state for iridium in the undoped case. So So it's still iridium 4 plus.
That means there are a lot of oxygen vapors.
Well, no. So the ruthenium is going in as 4 plus as well. So it's just isovalent substitution. Okay. So the final doping, or something we tried recently, since ruthenium goes in, it's isovalent, but it still has potentially a moment, S equals 1 moment. So we wanted to look at the case for purely non-magnetic substitution. So we looked at tin. Here are just some results where you can see there's a slight change in the lattice, and we can reduce the magnetic transition temperature, shown here. So looking at neutron diffraction measurements for 0.05 tin and 0.2, what we see is we get the same magnetic structure that happens to the undoped case when you apply a magnetic field. So we get a structural change, but it's distinct from the ruthenium case, and it matches the case for this 214 in applied field. So this is sort of, we published all this data, but this is sort of still ongoing work to try and understand the difference and exactly what's going on with the doping. Okay, so now if I move on to the osmium case, 5D3 case, sure.
Is the ruthenium doping case the only case when you dope some other certain when the spin is split into the edge one?
We have some data from manganese where we think that happens as well.
Also keeping the iridium as the charge state the same.
So manganese, I don't remember exactly if we checked the zones or not. So yeah, for the ruthenium we did polarized measurements to really try and track down, because I know the rhodium case, the picture is the spins lie within the AB plane, and they change. So
is it clear why ruthenium gives such a large spin gap?
no.
Single cycle isotropy or what?
Yeah, we just.
Ruthenium has no single cycle isotropy J1/2, but ruthenium is spin 1, so it may have spin single cycle isotropy. Is it because of that? Or?
It may well, yeah, it may well be. I'm not sure. Yeah, to model the data, we just put in a single ion anisotropy and then fit the.
40, the exchange constant is 42.
It's very large. Yeah. It's large. Yeah.
Really, same order, well, not even same order, but same number practically.
Yeah.
Okay.
Okay, so moving on to the osmium case. So here we're going over to this magnetically driven metal insulator transition. This is just the same slide I showed in the introduction part. Okay, so just a summary of this material since it's not been shown yet today. This is a perovskite PNMA space group, number 62. So it undergoes antiferromagnetic order at 410 Kelvin, so above room temperature. G-type ordering, every spin is oppositely aligned. From neutron measurements, we see a reduced moment of around 1 μb. Okay, and here's two plots showing the temperature behavior of, it's a little bit messy, this plot, sorry. There's an order parameter for the magnetic peak, and superimposed on top of that is, on the pink, is the phonon shift. So we see a large spin phonon coupling, and here is the resistivity, the gap opening as well, that all couples in together at this transition. So we have a lot of interesting behavior. So we wanted to try and follow the correlations through from the insulating state through to the metallic non-magnetic state. So these crystals are very small. To try and co-align enough of these for neutron scattering measurements would be not impossible, but take a lot of time and patience. So instead, we wanted to do resonant inelastic X-ray scattering. This technique relies upon it's element specific. So there's an iridium edge, but you have to develop different analyzers, slightly modify the instrument setup to measure at each of the different edges. So we worked with the instrument teams, both at the APS and the ESRF, to develop this for osmium, and we came up with a resolution of around 50 MeV, which is freely available to all users. And this is comparable to the iridium L edge. Okay, so here's the first results. These are just looking at the DD excitations, so essentially the orbital excitations. So this plot, if you look at it, the first peak is just the elastic line. Then we have one broad bump termed alpha. These are just transitions within the T2G levels, just spin flips. Then we have a beta, which is transitions from the T2G to EG. And higher up, you have more peaks, charge transfers. So this is from 10K through the metal insulator transition from the magnetic to the non-magnetic state. And these have just been offset by a factor. If we plot these real intensities, they overlap essentially exactly. So through the transition, we don't have any change in the local osmium ion. So, and we can fit this to this sort of crystal field plus Coulomb interaction model. where we can extract a Hund's coupling value, JH, of around 0.25 EV. So you can consider further splittings, introducing spin-orbit coupling. There is some osmium data that we took on a double perovskite, barium, yttrium osmium oxide, and calcium-3, lithium osmium O6, where you can actually resolve this splitting. But for this case, sodium osmium oxide, we don't see that, which may be due to the metallic nature, or at least the metallic boundary nature, or more likely the fact that the osmium ions are much closer together. So you get a lot of overlap. You're not really in the single ion limit. Okay, so now if we go and look at this low energy regime to try and see the magnetic excitations, what we see here in this data is spin excitation, so inelastic excitations. So I've labeled them here with the triangles. I know they're some a little hard to follow in the way this is plotted. And extracted the intensity here. So this is energy against momentum through the various high symmetry points. And what we can see clearly dispersing spin waves. So 5 minutes, great. So just to start to model this data, we applied a simple linear spin wave theory, J1, J2, with introducing just some any anisotropy to account for this large spin gap that we observe in this material. So again, we see the spin gap. We're measuring a large spin gap, but with a large instrumental resolution. So it's again down to fitting, but this is what we get out. So we see J1 equals J2 equals 14 MeV. That fits the data nicely. And there is some indication that we have a departure from this local moment model. As you go from the zone center out, you see a little bit of a broadening of the excitations, so a little bit of dampening of the excitations. Okay, so this was in 300 Kelvin, well within the magnetic regime. Now if we increase the temperature from 300 K to 450 Kelvin to the non-magnetic metallic state, you can see there's a clear change in the intensity of the scattering. Okay, so if we want to try and understand what's happening here, we can fit the model, we can fit the data to the magnon peak against some extra scattering that we see here in the green. So for the magnon peak, it behaves as you'd expect. It decreases in intensity until you get to the transition, and then it flattens off. But this other excitation starts to increase. And what's interesting is that the dispersion of both the magnon and this additional intensity we see around 0.1 to 0.6 disperses, they follow the same dispersion. So this is suggesting that it's not just a local, excitation, it's following the lattice behavior. Okay, so at high temperature, this material is predicted to be a Fermi liquid, at least from resistivity. So we tried just a simple Landau damping that didn't fit the data. So we went slightly beyond and looked at a weakly antiferromagnetic Fermi liquid model. This approach has been applied to unconventional superconductors as well, where you have this model and you can introduce some correlation distance, osmium to osmium distance, correlation length, and a damping coefficient. And if we put in these parameters shown in the brackets, you can see the solid line. We have very nice agreement to the data at various points in the Brillouin zone. So what we're seeing is that in the metallic non-magnetic regime, we have paramagnetic spin fluctuations with some correlations. They're weakly antiferromagnetically correlated. And so just the summary for this case is, as we go from, we start at 300K, the Heisenberg local moment model describes the data well, and then we have this continuous progression towards the itinerant limit where we can model the data with weak fluctuations. So this is quite an unusual observance just in one material. So I mentioned that you can have, this high temperature regimes following the similar behavior to superconductors, but for that you have to have various dopings and measure it under various different conditions. Here you can see the behavior just in one material. You can just tune it with temperature. Okay, and here is just the summary for the Strontium 2 iridium O4 case. And with that I'll end. Thank you very much.